Good morning, afternoon, or evening. How y'all doing today? And welcome to Mr. Morrow's Algebra 1 and 2 class. Today we're going to start talking about the real number system. But before learning about the real number system, let's talk about sets. What is a set, huh? Well, a set is a group of specific objects, okay? Specific objects, such as a set of plates, baseball cards, or numbers. And each object in that particular set is called an element of the set. And a subset of the set consists of elements from the given set. So for example, let's talk about subset here for a second. Let's say that you have a set of baseball cards. Now, in your entire collection, some are really valuable and some are not so valuable. So let's say that you want to just go ahead and isolate and pick out the rare, valuable baseball cards in your particular baseball set. Well, the rare cards would be the subset. So when you pull out the rare cards, you're defining the subset of your baseball set. Now, you can go ahead and list all of the elements of a set within braces. So this symbol over here is the symbol for braces. And these braces are going to surround the objects within your set. Now let's go ahead and start talking about the subsets of the real number system. Now the real number system encompasses all of these different subsets. So we're going to go from the inside out, okay? Now the first subset we're going to talk about is called natural or counting numbers. Now they're called natural or counting numbers because when you start counting, you usually count with 1, 2, 3, 4, and that is exactly what natural or counting numbers define. They're the whole units starting with 1. I want you to please make note of the fact that there are absolutely no fractions or decimals in natural or counting numbers. Now, throughout this lesson, we're going to be writing all of these sets in the form of an actual set with braces, and we're also going to go ahead and define them using a number line. Now, when you're plotting points, whether you're defining a number set or just plotting random values on a number line, it's pretty simple, and I'm going to teach you how to do it right now. So you just go ahead and you just are going to draw a straight line. And we're not looking for artists here. Just try to be neat. And in this particular number line, we're talking about natural and counting numbers, we're starting with 1. So there's a definite end to this, or actually beginning to this rather. There's an actual beginning to this. And that would be my first value of the natural or counting numbers, which would be 1. And then I'd have 2, and I have 3, then I have 4, ... And I keep going on forever. These 3 dots mean that that pattern is going to continue on forever. And at the end of my number line, I always like to draw an arrow. It's actually correct to draw an arrow because it signifies to the reader of this graph that this particular pattern of numbers keeps going on forever. If I was going to write this as a set, I would use my braces. Again, try to be as neat as possible. And the set of natural or counting numbers would include 1, 2, 3, 4, 5, 6, ... That's going to keep on moving forever. Okay? So it's pretty simple. When you're making your number line, you don't have to use these dots. You could just use a little tick mark if you so choose. And the idea of a number line is for the space between one interval or value and another are pretty much the same throughout. So this space should be equal to that space, which should be equal to that space, etc., etc. And that's how you create a number line and plot points. We're going to be doing a lot more of that throughout this lecture. Now, just to make it nice and neat, I went ahead and created them digitally, and this would be the number line of natural or counting numbers. and this would define the set of natural or counting numbers. Again, they are whole units starting with 1. All right, let's move on. Whole numbers. Whole numbers are whole units starting with 0. So in other words, you can go ahead and also say that the whole numbers are the natural numbers including 0. Okay? So they're whole units starting with 0. So in this particular case, my first number, the beginning of this set, is going to be, of course, 0, followed by 1 and 2 and 3, 4, 5, 6, dot, 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 and it's going to keep on forever. So whole numbers are whole units starting with 0, or in other words, they are the natural numbers including 0. The set of whole numbers would look like that. You have your braces, then you have 0, 1, 2, 3, 4, 5, 6, dot, 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 signifying that this pattern will continue forever. Integers. Integers are something we're going to be working with a lot, so please try to really focus up and understand what integers are. Integers are very simple. They're literally the whole numbers and their opposites. There are also no fractions or decimals. Okay, there are no fractions or decimals in natural numbers, whole numbers, or integers. There could be negative fractions and there could be negative decimals, by the way, but those are not known as integers. We're going to talk about those in a little bit. As far as creating a number line for integers, we have to place arrows on both ends of the number line. So in this case, we draw our line, but this time we want arrows on both ends of the number line because integers are going to go both to the right of 0 forever, representing all of the positive integers, and they're going to go to the left of 0 forever, representing the negative integers. So you would place your 0 here in the middle when we're dealing with a number line for integers. And if we go to the right of 0, we are going to increase value. We're going larger than 0. So we have integers such as 1, 2, 3, 4, dot, dot, dot. As we go towards the left of 0, to the left of 0, we are going smaller and smaller. We're going into the negative side of the integers. And it follows as -1, -2, -3, dot, dot, dot. Please notice that when we're dealing with negative numbers, the larger the negative, the smaller the value. The larger the negative, the smaller the value. Think about it as debt. Would you rather owe someone $1 or $100? Yeah, I think we would all agree that you would rather owe them $1, right? So the larger the negative, the smaller the value. Now I went ahead and created a nice, neat one here. So our number line would look as such, and my set is followed beneath. So the number line, again, we have our 0, 1, 2, 3, 4, 5. We're going positively. Okay, we're going to the right of 0, and that is gaining value, positive numbers. To the left of 0, we are decreasing value, -1, -2, -3, -4. Although the negative number is increasing in size, the value is decreasing because, again, the larger the negative, the smaller the value. Now, rational numbers are any number that can be written in A over B or fraction form. If you can write a number as a fraction, it's a rational number. Very important though, in this fraction form, the b, the denominator, cannot equal 0. Because if you have 0 in the denominator, for example, 5 divided by 0, that is what is known as undefined. Okay? Undefined. It just doesn't exist. 0 divided by 5, yeah, that equals 0. 5 goes into 0 0 times. But 5 divided by 0 is undefined. 0 goes into 5, never. It's impossible. It doesn't go in 0 times because 0 times 0 is 0. So you cannot have a denominator of 0 ever. Now, rational numbers include natural numbers. Why do they include natural numbers? Well, the example I'm going to give you is, let's say, 3. 3 can be written as a fraction, 3 over 1. Please remember that every number always has an invisible number being multiplied to it. So in front of this 3, there's an invisible 1 being multiplied to it. There's an invisible 1 being divided to it. And there's an invisible exponent of 1 up here. Please remember that. It's very powerful later on. So 3, even though it's a natural number, can be written as a fraction. So natural numbers are rational numbers. Whole numbers, same as a natural number. Let's say I write 0. Well, I can write 0 over 1. That's a fraction. So that is also a rational number. Integers, if I have -8, well, I can write -8 over 1. So that's a fraction. So that's going to go ahead and work as well. Of course, any fraction is rational, whether it is a proper fraction, such as 2/3, or an improper fraction, such as 3/2. Mixed numbers are also rational numbers because mixed numbers can be converted into an improper fraction. So 2 1/3, that's a rational number, okay? -5 1/4 is also a rational number. You may say, wait, but there's a negative. Yeah, that's fine. You can have negative fractions as a rational number. Terminating and repeating decimals are also rational numbers because you can turn those into fractions. If I have the terminating decimal, 0.125, well, I can write that as 1/8. If I have the repeating decimal, 0.333 repeating, that's going to be converted into 1/3. And last but not least, perfect squares are also rational numbers. And perfect squares are rational numbers because of the following fact. Let's say we have the square root of 81. Square root of 81 equals 9. 9 equals 9 over 1, so it is rational. So the basic definition, again, of a rational number is any number that can be written in a over b or fraction form, where b is not equal to 0. However, just to make it clear, rational numbers include natural numbers, whole numbers, integers, fractions, mixed numbers, terminating and repeating decimals, and perfect squares, such as the set below. So we have 5, that's a rational, 1.832, -3.222 repeating, 2/9 square root of 5, -1 7/8, -4, all of those are rational numbers. Now, how would I graph rational numbers? Well, rational numbers, you can't just shade everything because that's going to include all numbers, which also include irrationals, which we're going to talk about in a second. So when we're plotting rational numbers, we're just plotting the individual number in that particular set. In the set that I have here, okay, which I'm highlighting here in blue, I want to go ahead and graph each element of this set. So let's go ahead and plot 5. Where would 5 go? Well, 5's right here on 5. Except maybe we should make it +5. My bad. 5 right here. Then we have 1.832. Well, 1.832 is really, really close to 2. So it's between 1 and 2. So we're going to go ahead and estimate that that's about 1.832. Negative 3.22. Negative 3.22 is between negative 3 and 4, closer to 3. So we're going to estimate it at about right here. Okay, 2/9. How do we do 2/9? Well, we got to convert. So if you don't remember, you convert a fraction to a decimal by simply dividing. So if I take 9, the outside, place my 2 on the inside, that's going to be a repeating decimal of 0.22222 repeating forever. So 0.222 is between 0 and 1, closer to 0. 0.222 would be roughly about right here. Square root of 25 is, once again, 5. Negative 1 7/8. Negative 1 7/8 is closer to 2 than to negative 2 than negative 1. So we're going to estimate it about right here. And negative 4, of course, is a clear point right here at the negative 4 spot. Okay? So we have a little bit more practice of plotting numbers on a graph. Let's continue. Irrational numbers. Well, irrational numbers, okay, are numbers that cannot be written in A over B or fraction form. Irrational numbers include A, non-terminating or repeating decimals, such as pi, 2.332356, ... That means that it keeps going on forever. It doesn't stop, never ends. It's not repeating. Negative 0.6251417, ... That means it keeps going on forever. It's not repeating, and it never ends. It doesn't terminate. Hence, non-terminating or repeating decimals are irrational numbers. So non-terminating or non-repeating decimals are irrational. Now, I put pi here as irrational. Why is pi irrational, you may ask? Well, pi equals 3.14159265359 ... It keeps going on forever, and it does not repeat. So irrational numbers are numbers that cannot be written in A or B or fraction form, and they include non-terminating or non-repeating decimals that never end. They also include non-perfect squares, such as square root of 15, square root of 8, square root of 32. So all of these are going to be irrational numbers. Okay? And again, if we wanted to plot these numbers again on a number line, we're going to have to use some estimation. Okay? So pi is 3.14, so pi would roughly be placed between 3 and 4, somewhere about here, closer to the 3 than the 4. 2.332356 would be between 2 and 3, about right here. Not too much further because we're getting close to the half mark there. Negative 0.62514217 is between 0 and negative 1, closer to the negative 1, a little bit beyond the halfway mark, so it's about right here. Square root of 15. Square root of 15 is real close to the square root of 16, so that means it's pretty close to 4. I would plot that about here. Square root of 8 is really close to square root of 9, so that means it's really close to the value of 3, between 2 and 3, closer to the 3, about there. And square root of 32, it's actually closer to the square root of 36 than it is the square root of 25, so it's closer to 6. So we've got square root of 32 is between 5 and 6 here, and it's about here roughly. So you do have to estimate using logic and common sense. And now that we've gone over all of the subsets of real numbers, let's talk about real numbers. Because the real numbers encompass all of the subsets we just described. In fact, real numbers is the set of all rational and irrational numbers. In other words, real numbers are just about any number. However, little warning, there is also a set of imaginary or complex numbers, but we will get to that later on in the course. Now, as far as graphing real numbers go, you can go ahead and graph any particular value, okay, any decimal, any fraction, any mixed number, any perfect square or non-perfect square, because again, real numbers are both rational and irrational numbers combined. But when you graph all real numbers on a number line, it's pretty simple because it encompasses all of the number line. Any value on the number line is a real number. Any value on the number line is a real number. Okay, now let's practice. Using the key below, label the real numbers set or sets where each given number belongs. Let's use capital N for natural, capital W for whole, capital I for integer, capital R for rational, capital IR for irrational. So 2.6. Well, 2.6, it's a decimal, so it can't be natural or whole or an integer. But it's 2.6. It's a terminating decimal, so for sure it is a rational number. Now, we're not calling these real numbers because we've already defined that all of the examples below are real numbers. Number 2, -8. Well, it's not a natural number because it's negative. It's not a whole number because it's negative, but it is an integer. And since it's an integer, it's also a rational. Square root of 81. Square root of 81 equals 9. So that means it's a natural number. It's also a whole number. It's also an integer. Please be careful. A lot of times my students say, wait, how is it an integer? I thought integers were negative numbers. No, integers are whole numbers and they're opposites. So both positive and negative whole units. 9 is also a rational number because I can write it as a fraction. 15, pretty simple. It's natural, whole, it's an integer, and it is also rational. 22.364587934 ... It's not terminating, it's not repeating, so this is purely an irrational number. 11.526 repeating. Since it's a repeating decimal, it is rational. 2.78, it is a terminating decimal, so therefore it is rational. 0. 0 is not natural because natural numbers start with 1, but 0 is a whole number. It's also an integer, and it's also a rational number. Square root of 7 is not a perfect square, therefore I cannot place it in fraction form, therefore it is an irrational number. 33 1/4, it's a mixed number, it can be turned into a fraction, so therefore it is a rational number. Okay, hopefully you guys got the hang of that. Okay, let's move on. Using inequalities. Inequalities are used to compare the value of numbers. You have less than, greater than, less than or equal to, or greater than or equal to. When you're using inequalities, read the inequalities both from left to right or right to left. It really depends on you, the reader. For example, I can say 6 is less than 9. Okay, if I'm going from left to right. But I can also say from right to left, 9 is greater than 6. Okay, you can read it left to right or right to left. Just make sure that you're really focusing on the inequality. When you're dealing with variables and numbers, which we will deal with in great detail later, but I just want you to know that when you have a variable and an inequality and a number, you're reading from the variable alone. So for example, if I say x is less than 6, you read it x is less than 6. You can read it 6 is greater than x, but that gets a little bit confusing. So whenever you have variables, read from the variable. In fact, the variable may not always be on the left side. You can have the following. And in this case, you have x is greater than 7. So when we're dealing with variables, you read from the variable. When we're dealing with just numbers, you can go left to right or right to left. Now, a couple things that I would like you to really understand and remember throughout the course is the following. Let's say I have n is greater than 0. Well, I want you to really understand that this is just signifying a positive number. If a number is greater than 0, that means it cannot be negative, okay? It's greater than 0. It's a positive number. It's going to be greater than 0. So even if it's 0.000000001, that's already a positive number. So if I have n is greater, any value, actually any number is greater than 0, I have n is greater than 0, where n is representing a number, it's called a variable. We're talking about positive numbers. If I have a variable n and I state it to be less than 0, that means that we're dealing with a negative number. Because even if I have 0.00000, or rather, negative 0.0000001, that is a negative value. It's less than 0. When I have n is greater than or equal to 0, some variable is greater than or equal to 0, then this is what's going to be a non-negative number. Okay, it's a little bit different than saying a positive number. It's a non-negative number because n can be greater than 0, which is a positive number, or it could be equal to 0, and 0 has no sign. So n is greater than 0, it's a non-negative number, okay? When it's n is greater than or equal to 0, it's a non-negative number. It can be 0 or it can be positive, but for sure, it's a non-negative. If n is less than or equal to 0, kind of the reverse happens. This would be a non-positive number. Okay, it's going to be less than 0, so therefore it would be negative, it's not positive. Or it can be equal to 0, but again, 0 does not have a sign. It is neither positive nor negative, it is neutral. Okay, so let's practice this little skill here real quick. Compare each using inequality symbols. Well, I have -5 is less than -1, okay? I've got 12.3 is greater than 9.68. I have 3/5 is less than 7/8. Now, some of you may say, whoa, I understood the other ones, but how did you get that? Well, if we go back in time a little bit, you can compare fractions easily by cross-multiplying. If I say 8 times 3, that's 24. 5 times 7 is 35. Well, since 35 is greater than 24, 3/5 is less than 7/8, or 7/8 is greater than 3/5. Now for number 4, I have -9/10 is less than -2/3. If we use that cross multiplication skill, 3 times 9, it's going to be a -27 here, and 10 times 2, we're going to have a -20 here. Now, you may say, whoa, you got that wrong. 9/10 should be greater than, correct, Mr. Morrow? Because 27 is greater than 20. Well, not really, because we're dealing with -27, not a +27. So even though -27 it's a higher number, it has a smaller value because it's negative. Remember that the larger the number of a negative, the smaller the value. So yes, indeed, -9/10 is less than -2/3. And last but not least, let's discuss absolute value. An absolute value is the distance from 0. Since it is a distance, the absolute value of a number can never be negative, okay? There are no such things as negative distances. I have some scuba divers that always say, oh, but Mr. Moore, I always go, 30, 40 feet below the surface of the water. I'm going negative 30, am I not? Well, if we were to graph it, we would show it as you going below the surface of the water, which would be 0. So on a graph, you would see it as negative, but the real distance is positive. Just because you went 30 feet underwater does not mean that you went negative 30 feet. There are no negative distances. So absolute value is the distance from 0. Okay, and it's always positive. And absolute value is denoted by this awesome symbol right here. It's just 2 straight lines with a value, a number inside of that symbol. Okay, where n is a real number. If we look at absolute value again, just from a number line perspective, let's look at the absolute value of 4. The absolute value of 4 equals 4. Why is that? Because it's the distance from 0. So here at 4, if I go 1, 2, 3, 4 units to the left, I want a distance of 4. My absolute value of 4 is 4. If I go ahead and I want to calculate the absolute value of negative 4, well, go ahead and plot my negative 4 here, and that is also 1, 2, 3, 4 units away from 0. Okay, so negative 4 is also, the absolute value of negative 4 is also 4 because the distance from 0 is 4. Okay, so absolute value of 4, 4. Absolute value of 6.8, 6.8. Absolute value of 12, 12. Negative absolute value of negative 8. Whoa, let's see what happens here. This little negative really represents an invisible negative 1 being multiplied to that absolute value. So you can really read this as a negative 1, okay, times the absolute value of negative 8. Well, this will become negative 1 times the absolute value of negative 8, which is 8, and then negative 1 times 8 is negative 8. Now, I know what you're thinking. You said that you can never have a negative distance, that you can never have a negative absolute value. I did not lie to you. The absolute value of negative 8 is 8. Why did it become negative? Because of this negative 1 that I was multiplying. So if you see this down the line, let's say I have absolute value of 7 minus the absolute value of negative 3. Please keep in mind that this is the absolute value of 7 is 7. Drop that minus because it's a negative 1 that's being multiplied to this negative 3. So it's negative 1, right, times this absolute value of negative 3. So that'd be 7 minus 3, which would equal 4. So please be careful with that. Thank you so very much. I hope you learned a lot and have a great day. Bye-bye now.